Hey everyone, and welcome to today's Explainer. I am incredibly excited to guide you through a fascinating new frontier in science today. We're going to look at how the traditionally messy, unpredictable world of chemistry is entering a highly precise, completely digital era. Just imagine taking a really complex physical substance and perfectly translating it into a digital file. No, seriously, imagine that. That's the promise of what researchers are calling molecular informatics. It's a real game changer. And today, we're going to break down exactly how it works.
Okay, let's dive right into this. I know molecular informatics might sound like a highly complex academic discipline, but we've got a clear four-step map to guide us. First up, beyond single molecules. 2, the mathematics of messiness. 3, steps to digital reconstruction. And finally, chemistry's CAD era.
All right, part 1, beyond single molecules. To set the stage here, I really want you to ask yourself, what actually happens when chemistry truly meets the digital world? Just imagine if the complex, messy mixtures we interact with every single day, the coffee you drank this morning, the medicine you take, even the battery in your smartphone. Imagine if they could be perfectly digitized, analyzed, and reconstructed just like a piece of software. That's the core question driving this entire field.
So what are we dealing with? At its core, molecular informatics is a brand new, interdisciplinary science. But pay attention to what it researches: information representation, recovery, computation, design, and reconstruction of complex molecular systems. The absolute crucial takeaway here is that the focus is no longer on a single isolated molecule. No. Instead, scientists are looking at the massive, interconnected information of a whole system of molecules all working together. To bring this abstract definition down to earth a bit, let's look at real-world applications. We're talking about things like traditional Chinese medicine, the aroma of high-end foods, high-performance materials, semiconductor electronic chemicals, petrochemicals, the whole shebang. These aren't just one molecule. The scent of a high-end flavor or the conductive properties of a semiconductor material rely on a complex composition of literally thousands of molecules interacting.
So here is the huge paradigm shift. Traditional chemistry studies matter. It focuses on synthesizing and understanding single, isolated molecules. It basically asks, hey, what single molecule is this? Molecular informatics, on the other hand, studies information. It focuses on recovering and computing entire, complex compositions. It's asking, how do these thousands of molecules interact, and how can we map that system digitally? Moving right along to part 2, the mathematics of messiness.
Now, to make sense of all this chaos, we need a decoder ring. Look at how this brilliantly maps out where molecular informatics fits into the broader scientific landscape. Organic chemistry synthesizes molecules, analytical chemistry measures samples, AI learns from data. But look down at the bottom. Molecular informatics focuses on the complex composition. Its core task is to take all that data and recover the information, compute it, design it, and ultimately manufacture it. It's the missing link connecting analytical measurement, artificial intelligence, and physical manufacturing.
And amazingly, it all comes down to this equation. Think of this formula as the protagonist of our story today. C equals A times B plus error. It looks so simple, right? But this little mathematical formula is exactly what allows scientists to reverse engineer messy, real-world mixtures into precise digital data.
Let's decode this together. C represents the raw, messy experimental measurement data that the machines spit out. A is the composition information, basically how much of everything is in there. B is the pure molecular information, like the pure spectra of the individual ingredients. And is just the noise and system error we inevitably get in the real world. So the messy data, C, is literally just a combination of the pure ingredients, B, multiplied by their quantities, A, plus some background noise.
Which leads us directly to the ultimate brain teaser, the mixed signal inverse problem. See, in the real world, we only have C, the messy final measurement. That's it. The whole magic of molecular informatics is solving this inverse problem. It's the math of working backwards from the messy reality to uncover A and B, the pure, hidden, digital truth of the system.
All right, Section 3, Steps to Digital Reconstruction.
We know the math, we know the theory. Now, how does complex molecular systems actually undergo this digital reconstruction in the real world? Well, here's the 5-step pipeline that moves chemistry from physical trial and error to complete digital precision. It starts with acquisition, moves to recovery, then representation, computing, and finally, manufacturing. Let's break down these crucial steps.
First up,
Steps 1 and 2, which form our data foundation. Step 1 is acquisition. This is where scientists use highly advanced analytical tools, like GCMS or LCMS, to capture the raw data from a complex physical system. But remember, that data is messy. So that's where Step 2, recovery, comes in. This is where we apply that math formula we just learned. We solve the inverse problem to literally scrub the raw data, mathematically extracting the pure spectra, the precise concentrations, and the exact number of components. We're recovering the true, clean signal from the noise.
Once we have that beautifully clean data, we move to the digital brain, steps 3 and 4. Step 3 is representation. This means turning that recovered composition into a standardized digital object that a computer can actually read, search, and compare. Then, in step 4, computing, the real magic happens. Because the complex system is now fully digitized, scientists can perform similarity analysis, blend new mixtures digitally without spilling a single drop in a physical lab, and optimize formulas using algorithms. It's exactly like how architects use computer-aided design or CAD software to design a skyscraper before ever pouring an ounce of concrete. Finally, we reach Step 5, molecular information manufacturing. This is where we close the loop. The optimized digital design from Step 4 is sent back to the physical world to guide the actual manufacturing of the complex product. It goes from digital parsing to digital design to digital blending to digital verification and finally back to physical manufacturing. It creates a perfect, seamless, closed loop between the physical and digital worlds. It's brilliant.
And that brings us to Part 4, Chemistry's CAD Era.
Let's zoom out a bit. What we are witnessing here is a monumental shift. Historically, complex chemistry has been purely experience-driven. It relied heavily on physical trial and error in a lab, tweaking a formula slightly, crossing your fingers, and seeing what happens. Now, it's becoming data and computation-driven. Just as electronic design automation software revolutionized how we build complex electronic circuits, this data-driven CAD approach will forever change how we design complex medicines, advanced materials, and everyday products.
The ultimate goal of this entire discipline is unlocking a completely digital world of molecular composition. This allows us to take a complex physical substance and digitally store it, digitally search for similar profiles, digitally compute new interactions, digitally optimize the recipe, and digitally reconstruct it anywhere in the world. We are literally treating complex chemical compositions as if they were as malleable as lines of computer code.
There is a quote from the source material that captures this core philosophical shift perfectly. Chemistry past, what molecules are present. Chemistry future, how compositions are computed and reconstructed. We are truly standing on the brink of chemistry's future.
So, I'll leave you with this provocative thought. If the incredible messiness of real-world chemistry is being digitized, becoming as straightforward to manipulate as drag-and-drop computer code, what complex system would you design first? A new sustainable material? A perfectly customized medicine? The possibilities are quite literally endless. Thank you so much for joining me on this explainer today, and keep exploring.